In this example for constant acceleration in 2 dimensions, we're going to be jumping ravines. So you're trying to jump over a ravine in your motorcycle. The ravine has a width w, but the other side is h meters higher than your level. You launch with a speed v at an angle theta. We want to know, for a given angle theta, what is the maximum h can be such that the jump is possible. Also, for any possible jump, what is the minimum speed such that you just make it? Finally, for this set of parameters and a ravine depth of 100 meters, where do you land? All right, let's start with the picture. So I have a ravine of width w. The far side is a height h above where you start. Now you're going to launch with a velocity v at some angle theta relative to the horizontal. So what's going to happen? Hopefully, you'll follow some trajectory which will land you to the other side. We need a coordinate system. I chose the origin to be where you started, positive x to the right and positive y up. So what physics applies to this problem? Constant acceleration for sure. In fact, time isn't really discussed in this problem. If time isn't a part of the problem, I'm thinking of the projectile motion relationship that directly relates the y-coordinate as a function of the x-coordinate. Well, how would we use this equation? Let's look at the first question. For a given angle, what is the maximum h can be such that the jump is possible? Well, what does that mean? So it's launched, and okay, so you make that jump, but then it goes higher, and you keep raising h until at some point it's no longer possible to make the jump. What does that mean? First of all, if you just make the jump, if you're right at the limit, that means you're going to make it just on the edge, any less than you would have failed. That means that at the end, your y position is equal to h, and your x position is equal to w. So if we substitute those into the projectile motion equation, we get this. So now what can we do? So we've raised h some more. What can we change to be able to make the jump? Well, theta, w, g, all of those aren't changing. The only thing you can change is v. So you have to launch with a faster and faster speed as h gets higher. So how would we find the maximum h? You couldn't increase your speed anymore and make the jump. Well, that's the limit as v goes to infinity. Now, of course, we can't take the velocity to infinity. We can't go infinitely fast, but that's mathematically how we answer this question. What's the maximum height such that you can't increase the speed any longer? To find that, we take the speed to infinity. So to do that, v goes to infinity, and that term goes to 0. And we're just left with the maximum height is equal to the width, w, of the ravine times tangent theta. Does this make sense? Notice that this is a triangle where the opposite side of this right triangle is the height, and the adjacent side is the width. What does that mean? Well, that's a triangle where the hypotenuse is along the velocity vector. And that makes sense. If your speed really were infinitely fast, you wouldn't fall at all. You'd just go in a straight line directly to the point where you land. The next question is, okay, so you have a possible jump. What's the minimum velocity you need to have to be able to make it? Notice that the condition for that is still the same. The minimum velocity is going to be the one that just gets you to that edge, where y is equal to h and x is equal to w. So we can just plug those values in this time, and now just solve for v. To do that, I bring that term with the velocity on the other side, so it's positive, bring the h on the other side, and it's negative. Now multiply both sides by velocity squared, which brings it over here on the numerator, then divide both sides by this expression, and so now I get an expression for v squared, take the square root, and I'm done. The final question is, given these conditions and a ravine depth of 100 meters, where do you land? Now that's an interesting question. How would I know? Because I don't know right away whether I even make the jump, or if I fall, do I hit the wall, or do I land in the bottom? Well, let's take it one step at a time. The first question is, do we actually make it over here? Well, luckily, we found the minimum speed necessary to make the jump from before. And so we can just plug in the numbers and we can just calculate that directly. My calculator says that the minimum speed necessary to make the jump is 37 meters per second. So we fall. But now we have a new question. Where do we hit? Do we hit the wall? Do we hit the ground? Where? To answer that question, think about those two possibilities. One where the trajectory hits the wall, and another one where the trajectory hits the ground. And then try to create a mathematical representation of each of those conditions. What does it mean to hit the wall? If you hit the wall, that means when you've traveled a distance w horizontally, when your x condition is w, your y condition is not yet at the bottom, which means the y parameter is greater than a negative d. If by the time x crosses the ravine, your y position is still greater than the bottom, that's a mathematical representation of hitting the wall. What does falling to the bottom look like? Well, that says that when y reaches negative d, the x hasn't yet crossed the entire width. X is less than w. So if either of these are satisfied, then I know whether we hit the wall or fell to the bottom. And we can choose either one. I went with the first one simply because I thought 30 was pretty close to 37. Maybe we almost made it. I'm not really sure, but I had to choose one, so I went with that one. So here's the projectile motion expression where we have y as a function of x, and I'm looking for y where x is equal to the width, which is w. So I plug in those numbers and I can just go ahead and calculate it. The first term was 173, the second term almost 218. It certainly is negative, but it's a negative 44.6, almost halfway down, but still above the bottom, and so we hit the wall. Does this make sense? Well, I thought we would hit the wall because 30 is about 20% less than the minimum, but it still fell quite a ways. But since it hit the wall, which is what I expected, we have some confidence that it's right. The main key about this problem is that the equation was pretty simple, but you really had to understand what was going on in the problem and to be able to extract mathematical conditions for what the question was asking to be able to use the equation correctly.